Now we're going to learn about Archimedes principle. And Archimedes principle is one of the ones that I'm not that good at, but I'm gonna try to explain it anyway because it's coming out in exam, in the subjective questions. So first of all, Archimedes principle has something to do with buoyant force. So buoyant force is the force acting on upwards on an object immersed in a liquid when there is pressure difference between the lower surface and the upper surface of the object. So as you all know, the water pressure depends on the water pressure depends on how deep your water is, how deep you are in the water. So for example, here you are very deep in the water. So the height between you and the water and the surface is higher. So you will have a higher pressure. And then here has a lower pressure though. So because the pressure here is higher than the other, F2 is greater than F1. Therefore, the resultant force of this is the buoyant force. So F2 minus F1 is buoyancy, or FB. So buoyancy or buoyant force is upwards. Okay, that's the first thing. So yeah, buoyancy goes upwards, and the formula for buoyancy is rho Vg. If you wanna go and understand the formula, I kinda understand it. So but I am not going to try and explain this because I don't think we even have to know why it happens. You just have to know that the buoyant force formula is rho Vg here. Okay, let me just look at this again. Okay, yeah. I would like to explain this, but I want to save time as well. But okay, now Archimedes principle states that an object which is partially or fully immersed in water in a fluid will experience a buoyant force equal to the weight of fluid displaced. So if you were to put an object in the water, water will be displaced, right? That means some water, like if you were to put an object in the water molecules will be forced outwards like this. So that means there will be an extra the water levels will go up when you put an object in the water. It goes up because the water has been displaced by the object. So the buoyant force is equal to that weight of the water. So let's say you have here the Eureka can. So this spring balance is to measure the weight, right? To measure the weight. If you were to put this weight inside the water, it will displace the water out. So some water will go out. This is an Eureka can. So Eureka is from Archimedes. If your water gets displaced can, it will immediately fall out of the Eureka can into this electronic balance. So the total amount of water that falls out is the water displaced. So let's say so when you put the object in water, some water falls out, and then if you measure that water punya weight, it is the weight of water displaced. So yeah, wait. Let me just see. Record. Okay, and then kan, if you were to this spring balance, as I said, is to record the mass, right? It's to record the force. The weight of the object. So if you were to put the weight, if you were to put the object outside water, it will show a certain force, a certain weight. While then, if you put it in water, you will realize that the spring balance punya reading starts to drop. That means that the force, the weight, becomes lesser. So we call this the apparent loss in weight, because the weight isn't actually gone. The weight is just lost, or it's just gone, or it just disappears because there is another force acting on the weight, which is the buoyant force. And then if you realize properly, the weight lost from here, which is original weight minus apparent weight loss, is equal to the weight of the water. Yes, yeah. The difference between the weight of this is equal to the weight that you find here. So that is so buoyant force is equal to the apparent loss in weight. Why do I mean by that? Apparent loss in weight is the original weight minus the weight in water. So that is because the buoyant force changes the weight. It goes against the weight. So it reduces the weight. So the apparent loss in weight is caused by the buoyant force. So if you look at the next page, I think it will write, yeah, buoyant force is the apparent loss in weight. And we also know that the buoyant force is the weight of liquid displaced. So so the buoyant force is equal to the weight of liquid displaced, and is equal to the apparent loss in weight. That's why if you were to calculate the difference between the two weights here and the weight of the water here, it is the same, the exact same. So yeah, that's what buoyant force is. Now there are three conditions of state of flotation of an object in a fluid. Number one is the object is floating normally. Number two is the object is sinking. Number three is the object is rising up. So how do you know when is the object sinking, when is the object rising up, or when is the object in equilibrium? The object is in equilibrium when it is floating. When it is floating, the object is in equilibrium, which means that the resultant force is zero. Remember this, equilibrium means zero. Resultant force is zero, which means that the weight of the object is equal to the buoyant force. But wait okay, never mind. Okay, so again, the weight of the when the object is floating, the weight of the object is equal to the buoyant force. That means they perfectly respond to each other. If the weight is heavier slightly, if the weight is slightly heavier, then the resultant force will be downwards, kan? So that means the object will sink. So it will sink downwards with an acceleration of a. And if the buoyant force is stronger than the weight, like for example, if you put what I forgot the example. Okay, already. Wait, let me think of it first. Oh yeah, if you put you know those life saving vests, I forgot already. What's it called? Those round things. I forgot what they called already. Oh my god, I'm so dumb. Okay. You know those round things that you wear to that those babies wear at the swimming pool, kan? Like to make sure that they float. If you were to push this underwater, which I did a lot, you will realize that this thing goes back up very fast. And that is because the buoyant force is stronger than the weight. Remember that this thing is very light. The thing is very light. So it will have a low weight. But the buoyant force isn't based on the weight. It's based on the density of the water, the volume, and the gravitational force, rho GV. So there's no weight in it. So the buoyant force is not affected by the weight, but the weight is. So if the weight is very low and the buoyant force is very high, then it will go upwards. Yeah, then it will then the thing will go upwards. Then it will go upwards with an acceleration. So like if you have a very long tube, and then you put like you know how you put let's say in Minecraft you put an object here. If you put an object that can float, I think for example a stick. I think a stick can float. There are objects that can float, kan? They float when you put them in the water. They float slowly. So it will go up, then it will slowly speed up, and then it will become faster and faster and faster and faster. So it will become slow at first, and then it will go faster and faster and faster and faster. That means that it has an acceleration of a. Because remember, F equals to ma. Okay. Here's an extra part that you have to know. Forces acting on the ship are in equilibrium. The resultant force on the ship is zero. So again, weight of ship is equal to buoyant force. And then based on Archimedes principle, buoyant force is equal to weight of water displaced. So the weight of ship is equal to the weight of water displaced. So it says here, volume of seawater displaced is equal to the volume of the section of the ship immersed in seawater. So, how will I explain this? Okay. I guess the best way I can explain it is, remember that when you immerse an object in water, the water molecules will go upwards, right? It will go outwards, not upwards, outwards. It will like go all around, and then it will cause the level to go up. So that the volume of the total water going out of getting displaced is equal to the volume of the ship that's in water. Like for example, if I have this whole thing, immersed in water, then the total volume of water displaced is equal to the total volume of this whole thing. So I hope that's understandable. I don't want to get into the calculations because that's where it gets confusing. But yeah. Buoyant force is equal to the weight of water displaced. But if the object is floating, it means that maybe not the whole object is underwater. So wait, my bad. When you have a buoyant force, right? The buoyant force here is equal to the weight of water displaced. So if here is weight, then here is buoyant force. So if it's in equilibrium, then it's equal. So weight of ship is equal to the weight of water displaced according to the thing. If you look here, weight of liquid displaced, apparent loss in weight. Apparent loss in weight is the buoyant force. Wait. Apparent loss in weight. Oh yeah, because it's in equilibrium, the weight of the ship is equal to the buoyant force. And then as you know, the buoyant force is equal to the weight of the water displaced. Therefore, the weight of ship is equal to the weight of water displaced. So here's the thing. The volume of seawater displaced is equal to the volume of the section of the ship immersed in seawater. That's because no matter how dense or how not dense the object is, it's still going to take up a certain volume of water. And the volume of water that it takes up is equal to the volume of water that is displaced out. Because the water of volume, because when the volume of water that it takes here, the total amount of volume of water that it takes here is equal to the water that is displaced by the ship. Okay, I'm repeating myself now, but yeah, that's how it is. Even though the weight may be the density might be different, but the volume that is displaced stays the same. If I have a metal rod going into water, right? If I have a metal rod going into the water, and let's say it's floating this part of the thing, this part of the rod is now part of the water. The volume is still the same. Remember, the volume is volume is in cm cube. So it is base times height times length. So it's still this whole thing, right? The volume the volume is still this whole thing, including the thing immersed in water. But the thing immersed in water has already displaced some extra fluid. So this extra fluid that was displaced for water is equal to the volume of the thing submersed in the fluid. So yeah, basically, long story short, if I have an object in water, the volume of this is equal to the volume displaced. Okay, so I don't know if you should know the uses of Archimedes principle. I mean, this video is about these videos should be about the main tips, because most of you don't plan on getting like full marks anyway. But the main thing about this is you need to know the concept, and that is what I'm going to explain to you now. The thing is, right, the thing is, right, I heard that the question will be about a hot air balloon. This is about a ship, not a hot air balloon. So it might be a bit different. Before that, I want to recommend you to read more about it first. Go search about buoyant force in air, or buoyant force in air, or Archimedes principle in air, or Archimedes principle of hot air balloon, because apparently that's coming on exam. That's from what I heard from teachers. Okay. But yeah, let me see what it says. I'm gonna look at what it says first before I go to the hot air balloon stuff, because I already watched a video on it. Okay, so you know how the submarine works? Submarine works by using a ballast tank. So the ballast tank works something like this. Wait. Okay, so in a normal condition, the test tube is floating on water, and there is some trapped air in here. But then, if I were to compress this part, if I were to squish this part of the water bottle, it will cause the pressure in there to increase. So the pressure out there to increase. So high pressure to low pressure, that means water would be going in. Water will be going in. So when water goes in, that causes that causes the volume of water in here, the water level of the test tube to increase, because water goes into the test tube. Remember that this test tube is covered by masking tape, and masking tape is, I think, is semi-permeable. It is permeable, but not really. So only some water goes in. But when you push when you squeeze the water bottle punya part, it exerts pressure onto the test tube, so the water goes in by force. So that causes the water levels to increase. When the water levels increase, the weight of the water becomes greater, and therefore the total weight of the test tube increases. And because the total weight of the test tube increases, before this, the weight of the test tube is equal to the buoyant force. But now the weight of the test tube is more than the buoyant force. So now that it's more than the buoyant force, it will move downwards. Yeah, and then the hot air balloon. I'm gonna explain this later. I'll explain the calculation first. So now you learn buoyant force is equal to rho Vg